force, right? Time, okay. So this is the last lecture on dynamic programming, and then next week we will move into basically randomized algorithms, probability in, and randomness in algorithms for a couple of weeks, okay? And Ruta will, what happened here? Okay, all right. So what is dynamic programming, right? You know, it's a way to find efficient algorithms by coming up with a smart recursion that when you memorize it gives you a good algorithm, right? So it's built on recursion, and it depends on memorizing the recursion to come up with an efficient algorithm. And there are three pieces that I'd like to emphasize in that, which we already went over. One is, you know, how do you come up with, if you had a recursive algorithm, how do you think about the efficiency of the algorithm if you memorized it? So what does it mean? That means that you have to think what happens when I look at the structure of the subproblems. Are they many or are they small, right? And depending on the problem and depending on the algorithm, the number of subproblems generated by a recursive algorithm can be polynomial or exponential or something in between, right? So one task is to just given a problem and an algorithm, a fixed algorithm, understanding how it behaves. Okay, that's one basic task one needs to do, right? That we saw. You come up with an algorithm and then say, if I memorize it, it becomes efficient, right? The more difficult task is developing some intuition over time and with some experience and some examples, which classes of problems can we expect a dynamic programming algorithm to lead to an efficient algorithm, right? For example, we saw if you have tree problems, okay, trees decompose, so then maybe that is useful in doing dynamic programming, right? Or same thing, why does dynamic programming work on strings? Because strings are like decomposable, right? You know, you can kind of recursively decompose strings, you can recursively decompose trees. So that's the first cut idea, right? Okay, if I have a problem on trees, maybe I should try dynamic programming. If I have a problem on sequences, I should try dynamic programming, right? I mean, that's not the only reason. There are many problems for which dynamic programming applies where it's not obvious, right? But algorithms are not obvious, so we get more and more experience, we get to see more and more patterns, right? So that's a bit harder skill, but you know, that's part of being an algorithm designer is to get better at this, right? Okay, the last part is what I'm going to cover in today's lecture briefly is at first order, you know, dynamic programming allows you to see that a particular problem can be solved efficiently in polynomial time as opposed to brute force, right? Your first goal when you see a new problem, right, is not to find the fastest algorithm for it, but can I actually even find a polynomial time algorithm for it, right? That should be your first goal, right? Because, you know, for example, take sorting, right? Sorting, it is obvious that you can get a polynomial time algorithm. You don't have to be very clever to come up with some polynomial time algorithm, right? But the difficult part, why do we teach merge sort? Because okay, first, you know, 125 or the very basic programming, people teach bubble sort or selection sort or something because it involves no cleverness, it's very easy to analyze, and you get an n-square solution. It's something that people can immediately relate to, even on a layman can relate to bubble sort and selection sort. But then we say, let's make it faster, right? And we do merge sort or something like that, divide and conquer, right? There we are dealing with problems where it is easy to see it is polynomial time solvable, we are trying to make it fast. DP is one of the powerful techniques which allows you to actually see that a problem can be solved in polynomial time when it's not obvious, right? That it can be solved in polynomial time. But okay, your first goal should be, okay, I can solve it by dynamic programming. And the second goal is to make it faster, right? Okay, so that is what we'll focus on a little bit today. So how do you take maybe a dynamic programming algorithm and make it faster, right? Okay, there are two things you need to worry about in dynamic programming, not only time but also space. Okay, dynamic programming typically requires you to fill up this big table because you're storing all the recursive problems, and we already saw some simple examples where you can save space, right? And so we'll see, a generic technique in the context of edit distance, how saving space can be done not only for computing the value but also computing an actual solution. Okay, and there's a nice divide and conquer combined with dynamic programming allows you to actually compute the solution also efficiently and not just the value. Okay, that's a nice trick I would like you to be exposed to. And in the second part of the lecture, I'll give an example where once you figure out the dynamic programming solution, you can use some simple data structures to speed it up. Okay, just to sort of see, that's why people look more closely. Once you figure out the right solution, you further optimize it, right? And then you can get a faster algorithm. Okay, so let's go back to edit distance. Okay, we saw this edit distance. These are slides from a couple of weeks ago. We're given two strings x and y. We think of this as m letters, this as n letters, and we want to find what is the minimum number of edits you need to do to convert x into y, right? And it's better to think about it as an alignment problem, that you have a string x, a string y, and you want to align this string to that string, right? What is an alignment? Alignment is basically a mapping of this sort, right? You put letters on top of each other, you allow blanks also, right? And so an alignment consists of just this mapping, and the cost of the alignment is, if they are different, you pay 1, if they're the same, you pay 0, and if, that's you pay 1 if they're different, blank is different from any letter, right? And so that you count how many locations are the letters different, that's your edit distance. That's the same, right? So you think of it as an alignment, and okay. So we saw a basic dynamic programming algorithm based on the simple recursion that you peel off one character at a time, right? You say, okay, I look at x as a string followed by one character, y as a string followed by one character, and then what are the possible ways of aligning x and y? This big X and big Y, it is one of these three ways, right? Okay, and then you say, okay, if this is the way I'm going to align, I'm going to pay the cost based on whether X is not equal to Y, and then recursively align alpha to beta, right? And in this case, you pay 1 because you're deleting X, and then you align alpha and beta Y, and each case there, at least one string is becoming smaller, and so you're doing recursion, and this we saw, right? Yeah, okay. And then, we observed that if you do this recursion, the sub problems that you are generating when you start with x and y are the prefixes of x and y, right? And so there are only m prefixes of x, n prefixes of y, so the number of sub problems is m times n, so it's polynomial. You can memorize it, and once you identify that the sub problems are of the form ij, where 1 to I is a prefix of x and 1 to j is a prefix of y, we can rewrite the recurrence for each subproblem in this fashion, which is just what we saw. And the base case is one of the strings is empty, in which case the length of the other string is the optimum value, right? So this is simple enough. We saw this. And how long does it take? Well, there are nm subproblems, right? And each of them takes constant time to evaluate based on the previous thing, so it takes mn time, but it also takes mn space, right? Okay. So it's useful to visualize the computation, and these are old slides. I was dealing with a more general problem here. Let's call this 1, 1, and this is alpha xj is whether they're not equal, you pay 1, otherwise you pay. Okay, so it is useful to visualize this because I'll come back. The picture is very helpful, right? What is it? So this is x. And this is y, right? So you think of this as
x1, x2, xm, y1, y2, yn, right? What is this value? This is the optimum alignment. This is the optimum alignment between x1 to xi and y1 to yj, right? Okay, and you want to compute this, right? Okay, and to compute ij, you look at what? Opt ij is opt you one min of these three things. 1 plus opt ij minus 1, opt I minus 1j, and opt I minus 1j minus 1. Okay, you compute this value, and this is it. You can figure out this thing, right? Okay. You know, in general, if you are not interested in particularly in efficiently solving this, or you just say it's polynomial time, you say, okay, I have a mn time algorithm. How do you compute these things? You say, I'll just create the complete graph and just find a way to evaluate this using any topological sort of this DAG, right? At a high level, you don't have to worry about anything, right? Okay, but we want to do something a little bit more efficient, and then one thing we want to do is, okay, mn space is quite a bit, right? You know, if m and n are large, we're storing things. Do we need to store the entire thing to compute this guy, right? And we observed that, okay, you don't need to do that. What you can do is, suppose, you know, you want to compute ij, you do it in column order. Okay, suppose you want to do it in column order. That means, you know already all these values because this is base case, right? And then you will compute all these values. To compute all these values, you only need to know this column. And then you can throw away this column, because to compute all these guys, I only need to know this column, right? So at any point, you keep track of only two columns, right? And throw away the rest of the information. And eventually, you'll get to this value, right? Okay, that's good, okay. Okay, you can see the code for that if you are interested, right? So this is a summary of that, right? You know, you can compute the minimum edit distance in mn time and space. If you only want to compute the value, you can do it in O of m plus n space, right? And okay, now today what we're interested in is not to find just the value, but actually find an optimum alignment in addition to the value. Okay, is that okay? Okay, how do you compute the actual alignment, right? Yeah? Sorry? Yes, okay, so what is one obvious way, you know, how do you keep track of the alignment, right? You know, how do you compute the alignment? Yeah, one obvious way is to say, whenever I compute this, I'll keep track of the alignment, right? Okay, so if I knew the alignments of these three things, can I compute the alignment of this, the optimum value of the alignment of this? Because, well, I look at how I got here, right? You know, I took min of one of these three cases. I already have the alignments, and it'll tell me that, you know, the meaning of the, you know, if this was the min, it means that I am matching xi to xj, right? And I already have the alignment for the previous thing, so I can concatenate. But that takes, okay. So even if we did that, how much space do we take? Right? Suppose we actually want to compute the alignment. How much space would we take? So we can use the same space saving trick, right? But if you did the space saving trick, then still there's about say m plus n numbers m plus n entries we need to keep track of, and at each of them we have to keep track of the entire alignment, right? But the alignment itself takes m plus n, right? So even if you did this trick, but if you store the value of if you store the actual alignment at each node, it will take m plus n times m plus n. It's about mn again, right? So even with this trick, it is taking too much space, right? Okay, what is a way to, normally, you know, you don't want to store the entire alignment at each step. Okay, what you want to store is that, because you're copying a lot of information, right? What is a way to not keep the track of the alignment? We can just simply store at each point where we got the information, how we computed that, right? We say, look, you know, this was derived from this or this or this. We just keep track of 1 bit or 2 bits, right? Or the decision, right? If you did that,
But if you did that, then we keep back pointers, right? But if you did back pointers, then we need to keep track of the entire array, right? Make sense? Okay, so there is no easy way to actually compute the alignment in linear space. Okay? That's what I'm trying to get at. That if you want to compute just the optimum value, you can compute in linear space, right? But if you actually want to give the optimum solution, there is no easy way, or in fact, any reasonable trick doesn't give you a way to compute the alignment itself in linear space, right? Okay. Now, computing the optimal alignment is very important in many applications, right? You actually don't want just the value, but you actually want to compute the alignment, right? Typically, you want the alignment. So, what do we do, right? Edit distance is a very important problem in a lot of biological applications, a lot of other applications as well. And so, many years ago, actually, the Hirschberg came up with a very clever solution. But the clever solution is interesting not only because it's clever, and it solves a nice problem, but it's a very general technique, right? And there's a nice connection between most dynamic programming and divide and conquer, okay? So that's also something to keep in mind. So that's what we'll do today, okay? And one observation I would like to make, which we'll find useful, is the following, right? Remember, this, if you wanted to just compute this value, we said that we can just keep track of 2 columns, right? So we could also keep track of 2 rows, right, if you want, okay? But one nice thing that happens with that is that not only do you compute this value, you can compute all of these values, right, as well, and in linear space, right, because you kept track of the last column. Okay, that will be useful for us. It's a simple observation. Or similarly, if you want to compute all of these values, you can do it also in linear space. Right? Not the actual alignment, just the values, right? Okay, so that's good. Okay. So, what is today's clever solution is, you want to find an optimal alignment. It's actually, this is the wrong. You don't need the log factor. In linear space and O of m n time. Okay? Okay, so what is the basic idea? The basic idea is very simple. Okay? Okay, it is divide and conquer. Okay, so what is divide and conquer, right? We'll see here. So, fix some optimal alignment between x and y. Okay? Okay? So, I mean, there could be many optimal alignments, right? It's not unique necessarily, right? The value will be unique, but alignments could be. But let's fix one for simplicity. You can make it canonical in some way. Let's not worry about it. Okay, what does the alignment look like, right? It will map the first half of x to some portion of y, and the second half of x to some other portion of y, right? Okay, how does it look like? Pictorially, I want to break up x into 2 halves, right? This is 1 to m over 2, and m over 2 plus 1 to m, right? This is the first half of x and the second half of y, right? Where is y? Y is somewhere here, and this is y, right? So this is x, and this is y, and 1 to h plus 1 to n. Okay? So the optimum alignment of x to y, I can look at it and say, okay, what happened to the first half of x and what happened to the second half of x? Okay? Well, this got mapped to some prefix of y, and this got mapped to some suffix of y, right? That they together form y, right? But where, this h, I don't know, right? It can be, h is not going to be necessarily roughly half or anything, right? It could be all the way here, I don't know what that is, okay? Okay. Suppose I told you that, we can compute this, find the h such that the optimum alignment of x and y corresponds to mapping the first half of x to y1 to h and the second half of x to y h plus 1 to n. Suppose I can compute that index h fast. Okay? I'm only going to compute the index h fast. Okay? Right? Okay? So let's call that half of xy. What is half of xy? The index h such that the first half of x maps to y1 to h and the second half of y in some optimal solution. Okay? I am not going to be very fast with that, okay? Right, it's almost like computing optimum alignment, right? If I'm going to be able to compute that h, it more or less I have to compute the optimum alignment, right? Okay, I'm sorry, optimum alignment value, not the, right? So I'm only going to do it as best as I can do it with in just computing the optimum value, okay? But I'm not going to use more than linear space. That's the important thing, okay? So instead of computing the optimum value, I'm computing additional information, which is tell me the index such that, in that optimum alignment, this guy can be mapped to this and that guy can be mapped to that. Okay, what is the advantage of that? Once I have that, I can kind of break up the problem, right? If somebody told me that information magically. Okay, I'm giving you a lot of time to do it. How much time? As much time as necessary to compute the optimum solution value, which is O of Mn. Okay, okay. Suppose I had the subroutine for that. We'll figure out how to do that subroutine. Let's do what the natural divide and conquer strategy, right? Here is what I do. Okay, so I want to find the not the value, but I want to actually find the alignment, right? Okay, so if m equal to 1, what does that mean? Or m equal to 0, that means that one string is basically just constant, right? The other string can be large. In that case, I can just do the naive thing, right? The old algorithm will be giving you the alignment also, right? Yeah? Okay? Does that make sense? If one of the string is constant, you can just take the old algorithm and do the back pointers and you will get the optimum alignment. Not the value itself, but the alignment also. Is that clear? Yeah? Okay, if one of the strings is just constant, we are done, right? We don't have to do anything clever. Okay, otherwise what we do is we compute this h, the half xy. I'm not doing it very fast, right? I'm taking mn time to do it. But I'm only going to use linear space. And I'm just computing one value, right? Not, it's the index, nothing else, okay? Okay, once I find that, I recurse on, I know that, I'm going to align the first half of x with y1 to h, right? I know the value h. And then I'm going to map this guy to y h plus 1 to n, okay? Okay, now, it's very important that I sequence these recursions. Okay, we'll see why. Sequence the recursion in the following sense. While this guy is running, he may use some more space, right? But I don't run them in parallel. Okay. And so this guy is actually going to compute the alignment itself, not just the value. It's going to compute the alignment for me. So what is the alignment for x and y? Once I have the alignments for the first half of x and the second half of x, I just put them together, right? Yeah? Agreed? So that's the algorithm. We don't know what the running time and the space of this is. Okay? Is that clear? Okay. So any questions on the algorithm? Right? Okay, I'm doing extra work, right? Because I'm first computing half and then I'm recursing again. Even though I know the optimum value, I'm again going down, and this is all just to save space. Okay? Okay? Yeah?
Are you using time
No, sorry, am I using time what?
Time for space.
No, I'm not going to even lose time. Yes, yeah, this looks like I'm wasting time to save space. Now the question is how much time am I wasting, right? If it is, sometimes it's worth wasting time if the space is really a premium, but we will see that this is not going to cost me much more extra time. Okay? Okay, we'll see that divide and conquer helps us, right? Okay, because the problem is getting down by half. Okay, the correctness of this is clear, right? Because by definition half xy is giving us the right answer. If you assume half xy is giving you the right answer, this is correct, right? Okay? Meaning, yeah, we're doing something the obvious thing. That's the whole point is that half xy is giving the right answer. So there must be an optimum alignment of, yeah.
I'm not sure why the combination is obvious, combining the two halves.
But that is the definition of the half xy, right? Because what is let's go back, right? That's important to understand, right? What is half xy is defined to be the index h such that the optimum alignment of x and y is composed of the first half of x matching to the y1 to h. So
by definition, that is the there is an optimum alignment which aligns x1 to m over 2 to y1 to h, and x m over 2 plus 1 to m to y h plus 1 to n. So if I give you that h, you know that there exists an optimum alignment to do that, right? So I am finding the optimum alignment for each of those and I am putting them together. Maybe I know it. Are you questioning whether there exists such an h?
Yeah, questioning how put together the thing would be optimal to the whole 1 to n.
Oh, okay, so then maybe the confusion is that can every alignment between x to y be thought of in this way? Yeah, but what is an alignment between x and y, right? It is just mapping the characters of x and the characters of y in some fashion, right? So, but the alignment means that you cannot, the definition of an alignment is that you cannot cross like this, right? In an alignment, you cannot have, for example, where is this? If you go back to the definition of edit distance, maybe that's where the confusion is. If you go back to the definition of alignment, which I didn't go over formally, right? What is an alignment is a set of pairs ij such that, so basically it's like pictorially, you can't map this guy to this guy. It is, you basically, what is this doing? It is taking, FO is being mapped to MO here, and OD is being mapped to NEY here, right? So the alignment is in this fashion, but because of the gaps, you just have, if I ask you what did foo map to, right? You can map it to foo, can map to MON, and D maps to EY, right? That's what is the definition. Okay, you can't have crossings of the alignment. Okay, so that's why you can put them together, right? In fact, that's the reason why, in fact, the problem decomposes. If they can cross, you cannot do that recursion. Okay. Let's see. Okay, where are we? Okay. Okay, the correctness is basically based on that definition of H. Okay. Okay, what is the running time of this algorithm? We are spending more time, right? So I claim by divide and conquer, when we'll see the proof, that we don't spend more than mn again. Why? Because each problem we're cutting down by half and the geometric series kicks in, and we'll at most spend 2 times mn. I mean, there's a constant there, but we'll see the proof of that. It's not hard. Okay. Okay. And I claim the space is basically O of m plus n. Okay. Okay. And that is based on this being true, and this is the hard part, and we'll come back to how to do this. But let's first understand that this divide and conquer gives us the right time bound and space bound. Okay. So why is the time O of mn of this algorithm? Well, it's a recursive algorithm. Let's not think very clearly. We just write a recurrence based on what the recursive algorithm is doing, right? How do we analyze the running time of a recursive algorithm? We just plonk down a recurrence, right? And then see what it does, right? Okay, what is T of mn? Well, what does the recurrence say, right? If m equal to 1, what is the running time? O of n, right? Well, it's the base case, it's right. So the recurrence for the running time is T of mn is constant times m if n is small, n is constant, is C of n, I'm using the same constant because we can take the bigger of all the constants, okay? If m is less than or equal to 1, otherwise what is it, right? Otherwise it is T of m over 2 h plus T of m over 2 n minus h, right? We broke up x into equal pieces, right? We are mapping the first half of x to y1 to h, right? So it is T of m over 2 h plus T of the other half to n minus h plus how much time did we spend? Mn time, right? To compute, I told you that half takes some mn time, right? I haven't told you how to do it, but I guarantee to you that half will take only mn time. So this is the recurrence, right? Okay. So I claim that the solution to this is 2c times mn. Okay. So it's doubling the cost, right? So but that's not very hard to see by the, which way do you like to see the proof?
Okay. So there, I mean, you can prove it by induction. Okay. It's very easy to prove it by induction, but that doesn't give you much intuition of why it is actually right. So with experience, you don't even think why it takes mn time, right? Because in fact, the design of the algorithm, the thinking about divide and conquer was based on the idea that okay, if you break it up into half, it will converge, right? So so it's almost like the analysis will guide you how to think of an algorithm, right? But since okay, let's see why I like the recursion tree method, right? Okay, what is happening here? You have a problem of size what? Mn, right? What did you do? You broke it up into two problems, right? It's a little bit trickier because there are two parameters here, right? And it's a little unclear what is happening. M over to h and m over to n minus h, right? Okay. And then this guy goes into m over 4, and one thing to notice why it's a little tricky is that you have no control over h, right? It can be any h depending on the problem. It could be, right? So that seems like a little tricky, right? M over 4 some h prime, and m over 4 some h minus h prime, so it looks complicated, right? Okay, but let's see, how much time do you spend here? C times mn, right? Right? In addition to putting the thing, you print. Okay. Okay. So how much time would you spend here, right? Well, you would spend C times m over 2 times h, right? Here you will spend C times m over 2 times n minus h, right? Okay, and so on, right? So let's just add up. I mean, so if you want to compute the total time, you have to add up all these numbers and see how much that is, right? Okay, but at the second level, let's just do one second level. How much are you going to spend here? It is C times m over 2 times h plus C times m over 2 times n minus h, right? So this h and n minus h together add up to n, right? So you get, what do you get? C times m over 2 times n. Yeah? So if you look at the picture, if you add it level by level, you have C times mn. Here what do you have? C times m over 2 times n. At the next level, how much will you have? Times n. So what do you get when you add it up?
Geometric series.
You get a geometric series, right? So it will be 2 times Cmn, right? Okay? Okay. So it's not, it's a very easy thing. It is the same thing, you get when things converge. Right? If you cut down the problem size by half and your work goes down by half, you will converge to the top level. Okay? Okay? It's just the fact that there's a second parameter is a little bit confusing, right? But it's not, once you get the hang of it, it is the same geometric convergence. You can even prove it by induction, if you guess it, you can prove it by induction. That's there in the slides. Okay? Okay? So we have not increased the time by too much, right? Okay? So that is good. What about the space? How much space are we using, right? Okay. Well, what is the space usage? Space usage is a little trickier to even understand what is the space usage of this, right? We say, okay, look, Smn is a space. So here is what I claim. What does the algorithm do, right? The algorithm uses some space to do some local computation, and it also is writing the final answer in some it updates the actual alignment, right? Let's not count the time it takes to do the actual alignment, because that we can fix the size of the alignment is m plus n, right? It doesn't override that, it just uses that as output tape, right? The only thing we have to worry about a little bit more is, locally how much time is it spending, right? Because the algorithm is calling itself recursively, many times and stuff like that. Okay, I claim if it is making two recursive calls, right? Okay. I claim it takes the max of these three quantities. Okay. No more, and plus some constant space. Okay. What is the, see, it is making two recursive calls, right? Okay. So once the first recursive call is done, it doesn't have to actually store the space for the recursive call. Okay, look at the recursion tree, right? How does the algorithm proceed? The algorithm proceeds by doing this, right? It starts out here, it calls this guy, and this guy will call something, and this guy will call something, and when it comes back, what happens, right? It used some space here, right? When this call, say for this guy, when this call is finished, the auxiliary space that this guy is using doesn't have to count towards the space of this guy because you can release that, right? Okay, so but what happens when this guy returns? This guy will write the alignment for this half in the global array, but that array is fixed, right? We don't count that in our space usage because we'll separately count for it, right? Because we only write on that only once, right? Okay, so that is m plus n, right? The final output mn, we keep separate storage for that, right? We don't use that again and again for any purpose other than just to store the value, right? So when this guy comes back, it writes in the m over 2 is aligned to 1 to h, and we're done with that, okay? But what we are worried about is that, when this guy calls this guy, you have to store something in the stack, right? And this guy stores something in the stack, right? How much will that extra storage be? I claim it is not more than this, right? Whatever this call takes storage, whatever this call takes for storage, the max of those two because we can release that, and c times m plus n because that is the time it takes for the half to compute, okay? And then plus we need to keep track of some constant number of counters, right, to keep track of basic information. Not more than that. Which index we stored and which. So if you do that recursion, then basically you will get that the total space used by this is c times m plus the depth of the recursion, which is only O of log m. Okay. Okay. So you have to convince yourself that this is the right expression. Okay, it's actually just look at the recursion. We free up space as we come back up. You don't need to keep. But if you do it in parallel, you can't do that, right? Because they'll all be using space, right? Even if you do it in parallel, the space usage will only go up by log m factor. Okay, that also you can check. But the space is actually good. Okay. Now the main thing that we need to worry about is how can we magically calculate this half xy? Okay. Remember, right? We want to know what is the definition of half xy. You want to compute an index h, right, such that the optimum value of the edit distance between x and y is equal to the edit distance between the first half of x and y1 to h, and the second half of x and y h plus 1 to n. Right? There could be many h values like that. We want to compute at least one of them, right? That's our task, right? How do we do that, right? Okay, that seems hard to do, right? How to compute that h? Okay, so instead we'll do something, simple, right? So we say, okay, I don't know what that h is, right? Okay, so I'll say, okay, for every value of k between 1 and n, compute the edit distance between x1 to m over 2 and y1 to k. I don't know the h, I'm trying to find that h, right? Instead, compute for every k between 1 and n, the edit distance between the first half of x and y1 to k. So k equal to 1, I'm not computing one value, but I'm computing n values. Okay. Similarly, I say, okay, for every value of k, compute the edit distance between the second half of x and yk plus 1 to n. Okay, and then choose among all the values of k the minimum k. When you add them up, you get the smallest value. My claim is that will be the value of h you want, right? Okay, so pictorially, what is it trying to find, right? We are trying to find here. Let me use this picture. Okay, so what are we trying to find? We want to say, okay, this is x and this is y, right? And we're saying, okay, I'm going to break up x into two halves, the first half and the second half. Okay, I'm saying, okay, now let's look at k here. Okay, and I say, okay,
map this half of x to y1 to k, this half of x to y k plus 1 to n. Okay, do that for every value of k and find the minimum value. Okay, that would be the, for a fixed value of k, compute the distance between x half and y1 to k, and x the other half, right, x half plus, I'll say, y k plus 1 to n. So if I know both these values, I will know the way to align using k, and if I minimize over all k between 1 and n, I will get h, right? Yeah, that is a definition of h basically. No, that's not clear? Okay, what is the definition of half xy? What is the definition of half xy? Yeah, what is the meaning of h? Yeah, so okay. So let's take any optimum alignment between x and y. How does it look like? Right? An optimum alignment of x from y can be broken up into an optimum alignment of x, the first half of x, to some prefix of y, and an optimum alignment of the second half of x to some suffix, the suffix of y, right? Where to do that, I don't know, right? I want to find one, there could be many different values. Let's say there's only one nice breakpoint, right? I want to find that breakpoint, right? How do I find the breakpoint? It seems like it is hard to find it, so I'll do the dumb thing. Right? I'll say, okay, try all breakpoints. If you break up y into y1 to k and yk plus 1 to n, map the first half to this piece, second half of x to this piece, and compute the value of doing that alignment. And do it for all values of k and take the minimum. That will give you the optimum alignment, right? That's all I'm trying to do, right? Okay? So the only question is, that seems like expensive, but here is a nice thing, right? What are we trying to do now? Remember that you want to compute for every k the edit distance of the first half of x and y1 to k, right? If you do it in a silly way, you will take a lot of time, right? But I claim that this is very nice because, okay, I want to compute, let's look at the first piece. I want to compute the edit distance of the first half of x and y1 to k for all values of k between 1 and n, right? Okay, but what if I did the edit distance of x, the first half of x, and the entire string y? While computing the edit distance between x and the entire string y, I claim I'll actually compute all those values because I need them in my recursion. Okay. Okay, so remember what I was trying to do? I just compute the edit distance between the first half of x and y now. Okay. While computing that, I claim that we will compute all of these values, right? Okay. Okay, what does it mean? Let's go back to the picture. See here. So what does it mean pictorially? When I compute the edit distance between x and y, okay, what is the meaning of this column, this value? What is this value? Opt opt m k. What is the meaning of this value? This is the optimum edit distance between the entire string x and the prefix y1 to k, right? To compute this value, in fact, we have to compute this entire matrix, right? But in fact, in particular, to compute this value, we are computing all these values also, right? But what are these? This is the optimum value of matching the entire string x to each of the prefixes of y. But that's precisely what we want, right? We want to find the optimum value of matching x1 to m over 2 to y1 to k for k equal to 1 to n. But that simply the middle row of this matrix is precisely what we want. Yeah? So I'm replacing this m by m over 2. Think of mapping the first half of x to the entire string y and take the bottom row of that computation. That gives us all the values of what we want, right? It is the optimum value of matching the entire x to each prefix of y. Okay? So we know this entire, we just have to keep track of the bottom row, and we know we can do that in mn time, but m plus n space, because we are going to keep track of that entire row anyway, right? So that means that when I compute so one half of that is easy, right? So if I want to compute edit distance of x1 to m over 2, that's just a fixed string, right? We know that fixed string, and map it to y1 to k for each value of k, I just compute the edit distance between the first half of x and entire y and keep track of the bottom row. Okay? So I have all those values, right? How much time did I spend? M over 2 times n, but space is linear still, right? M plus n, right? We didn't use extra space because we kept only one row at the bottom row, right? Okay. Now what do we need? We need the slightly different thing. We also need the following piece of information, right? For all k between 1k and n, I want the edit distance between the second half of x, right? And the suffixes of y, right? yk plus 1 to n. This is a bit tricky. They are not prefixes, they are suffixes. Okay? Okay. Okay. So this looks a little difficult, because suppose we did what we did in the previous trick. If you computed the edit distance between the second half of x and the entire string y1 to n, what does the bottom row give us? Bottom row gives us the edit distance between the first half, the second half of x and y1 to k for all k. It is giving us the prefixes of x, but we want the suffixes of prefixes of y. We want the suffixes of y. This seems a little tricky. Okay? So pictorially what is happening is the following, right? In the previous case, this is the first half of x, right? And this is y. Okay? If you computed, this is x1 to m over 2. If you computed the edit distance between this guy and the entire guy, I can compute, it gives me as a bonus the distance between this string and every prefix of y. Okay? Okay, but if I did the same thing and say, no, I want to compute the edit distance between this guy and the entire y, it will do the same thing, it will give me the prefixes of y. But I don't want the prefixes of y, I want the suffixes of y. Okay? So what do I want? I want to map this guy to this for every value of k, right? So, okay, so you need one more trick, okay? It's a very simple trick. You observe that the edit distance of xy is the same as the edit distance of the reverse of x and y. Okay? If you take x and y and compute the edit distance, it's the same as reversing the strings and computing the edit distance. You are looking at the alignment from the other side instead of looking at it from this side. Okay? Do you believe this? This is not hard to convince yourself. Yeah? Okay? Okay. So that's it. Instead of doing edit distance of, you just reverse the second half of x and reverse y and compute the edit distance, and that will give you the right information. The same trick we used for the first half of x and the entire y, you apply to the second half of x and entire y, but you first reverse both strings, and then you will get the right information. Okay? Once you have the right information, you check for each value of k, you compute the minimum, the sum of them up, take the minimum over all k, and that will be your h. The one which achieves the smallest value will be the h you want. Okay? So how did we compute half xy? We computed the edit distance between the first half of x and entire y, right? Using what? The space saving algorithm, right? Okay, but along the way we got the bonus that we got the entire bottom row, so that we could get for all values of k, not just the final value. We got the entire bottom row, so that helps us. And to compute the second thing, we took the reverse of the second half of x and the reverse of y, and again stored all the one row, and then we matched up for every value of k. You compute the sum of these two to minimize it and get the right value of h. Okay, you can see the total time is basically mn, right? Because we are doing edit distance computations, and we store two. Basically, we have to store two rows basically. Okay, this is just to compute that index h, and then we do the divide and conquer. Okay, all right. Yes, it's tricky, no? It's not so obvious, right? Yeah. So this is a divide and conquer algorithm to compute the optimal alignment in mn time and m plus n space, right? So it built on computing the value, and then once it is a generally applicable technique. So for many problems where if you can save space to compute the optimum value, you can save space to compute the optimum solution. Okay, but this is how you do it. But this is an illustration of that. Okay. Questions? I know it's a little tricky to think about this. You have to go back and convince yourself that, yeah.
It's probably a trivial issue, but when n is an odd number,
yeah.
the middle element needs to be...
When m is an odd number. You can always assume it's the power of 2 by adding dummy things or something. Or I have to be a bit more careful with the indices, floors and ceilings. Then everything will overflow and you won't understand what is on the slide. Yeah, that's just a minor technicality. Okay. Yeah, any other questions? Yeah, seems okay. But divide and conquer is a very powerful technique. Okay, we are combining divide and conquer inside the dynamic program now, right? So it's an optimization once you figure out the right structure, right? Okay. Okay, we will do quickly a second problem just to. It's a very simple problem, very classical problem. I want to illustrate some data structure trick again. Now here we're trying to improve space, time, not space. Okay. Okay. Longest increasing subsequence, right? It's a very nice, simple problem. So I give you a sequence of numbers, right? Let me dispense with the easy definitions that you're familiar with. I give you a sequence of numbers, and I want to find a subsequence which is increasing. What is subsequence? I drop some things, right? So, so here, I got 5, 2, 1 is a subsequence, right? So a subsequence is called increasing subsequence if all the numbers are going up. Okay. It is decreasing if they are going down. Okay. Okay. So given a sequence, the goal is to find the longest increasing subsequence. Okay. Right. So if the entire sequence is increasing, you have to give the entire thing out. Right. If the entire sequence is decreasing, what is the optimum value? Sorry? If the sequence is decreasing, what is the optimum value? 1, right? Yeah, okay. Just to test that you understood the definition. Okay, so that's the problem, right? Given do you know Dilworth's theorem? There is something very famous result in this sequence is called Dilworth's theorem, that you can ask, clearly, if the sequence is increasing, if the sequence is decreasing, the optimum value is 1, right? So there is not very, okay. So here is a nice question. If I give you a sequence of n integers, will there always be a very long increasing sequence or a very long decreasing sequence? Right? Just a pure combinatorics question. Does that make sense? The question. See, clearly if the sequence is decreasing, the increasing sequence is only of length 1, right? But then you have a long decreasing sequence, right? So a nice question to ask is, will there always be a long increasing sequence or will there always be a long decreasing sequence? How long can we always guarantee that, right? So Dilworth's theorem says that in any sequence of n integers, there is always a sequence of length at least square root n which is increasing or is decreasing. And that's tight. You can easily create a sequence which has both increasing and decreasing sequence of length only square root n. But Dilworth's theorem says that it always exists a subsequence which is either increasing or decreasing and has length at least square root fn. Okay, that's a famous result in combinatorics called Dilworth's theorem. Okay, It's used many times in algorithms. Okay, anyway, we are not interested in that problem. I give you a sequence, I want you to find the longest increasing subsequence. Okay, it's a very classical dynamic programming problem. There are several different ways of understanding the recursion. I won't go into the development of how to think about this and stuff. I'll give you one solution, right? And then we'll figure out how to optimize it. The goal is to figure out how to optimize it. Okay. So this is a little bit non-obvious solution, in fact, right? So let me define the following quantity, right? It is given a sequence of length n, say it is stored in an array A. Let's look at length of the longest increasing subsequence that ends in the last guy. I'm not interested in the longest increasing subsequence, I am interested in the longest increasing subsequence that ends in that guy, the last guy. Okay? It makes actually writing the recurrence much easier than if I wanted to just write the longest increasing subsequence. Okay? So, I mean, I don't have time to explain why it is interesting and stuff. So I can write a recurrence for this, right? What is the length of the longest increasing sequence ending in the last guy? How do I find it? I want to include that guy, right? That's what the definition is. So I add 1 to myself, but then I go back and look at everybody who is smaller than me. If there's anybody who is smaller than me, I look at longest increasing sequence ending at that guy and add 1 to that, basically. Right? So this is the max over all I such that a of I is less than a of n, 1 plus LIS ending a 1 to I. Okay? Is that recurrence clear? Yeah? Yeah? Okay? Okay. So then finally, okay, and so let's do this on a quick example. Okay. So what is the longest increasing sequence ending at 6? Just 6, right? So 1, right? What about 3? 1, right? Because there is, right? What about 5? 1, right? Yeah? Huh? Okay, that was 2, right? Why? Because you can go back, 3, 5 is an obvious answer, right? You know. Okay, but what about 2? 1. What about 7? Okay, now it's like, oh, we have to think, right? Well, let's not think, let's use a recurrence, right? Okay, so we go to 7 and say, okay, if I go to 5, I get 3, right? If I go to 2, I get 2. If I go to, sorry, I should have gone this way. I go to 2, I get 1 plus 1, 2, right? If I go to 5, I get 2 plus 1, 3. If I go to 3, I get 1 plus 1, that's 2. And if I go to 6, I get 1 plus 1. So I get 3, right? Okay. For 8, what do I get? 4, okay. For 1, I get 1, and for 9, I get 5. And okay, what is the longest increasing sequence? I have to take the max of all these values, not the last guy. Right? Yeah? Because what if I sequence this with 1, right? Then I will get 1, but then I have to take the max of all these guys. Right? Okay. Agreed? Okay, so it's easy enough. So how many sub problems are there as I compute these guys? And right at each, we just computing, we say went along the sequence, right? We have to store all those values, right? Okay, so and then we enter return the thing. Okay, okay. What is the running time of the algorithm, though? N square time it takes, right? Why? Because to compute the value at one guy, I have to go back in all the previous guys, look at all the guys who are smaller than me, right? And add 1 to them if they are smaller than, right? You know, so I can take n time to do it, right? And you can easily create an example. Suppose in fact the sequence is increasing, right? What will you do? You'll look at this guy and keep I have to look at everybody. I have to compute, right? Right? It will take n square time. Yeah? So space is n, time is n square. Okay, and then what do? You say, okay, can we improve the running time of this? So that's the question we are asking ourselves. Right? Okay? Agreed? Okay. So what does it mean to improve the running time, right? Well, you can change the algorithm and improve the running time, right? But that's not what we're looking for typically, right? When we say we're improving the running time of a dynamic programming thing, we're saying, can we follow the recursion and compute the things that we want to compute faster than the obvious way, right? Okay. So what are we trying to compute, right? This is right. So what we want to compute is, when I want to compute the value of the ith guy, what am I trying to do, right? I want to look at all the guys who are before me, who are smaller than me, right? And look at their values and take the maximum one of them, right? Right? That's what I want, right? Okay. Now the thing is, can we create a simple data structure that will allow me to find that maximum faster than by just looking at all of them? Okay. So that's what we're looking for. Can we create a data structure, or can we use an existing data structure? Let's not create something funky because that's hard, right? What data structures do we need? Say, okay, we know search trees, we know heaps, priority queues, maybe things like that, and say, can we use one of them and maybe tweak them a little bit to help us make this computation faster, right? One thing we realize is that we need the data structure to be dynamic, right? Because once I compute the value of the ith guy, I want to put that information in the data structure so that it will help the next guy, right? So we need at least some dynamic data structure. We can't just use some static structure, right? Okay. So can we think of a simple data structure for this? Okay. So I claim we can try to use binary search trees. Okay. What is the first thing we need to do, right? When I want to compute the value of the ith guy, what do I need to know? I should look only at numbers in A1 to I minus 1 that are less than me, right? That itself is not obvious, right? If I want to take a number AI and I look at only numbers smaller than me, right? And then I have to check what their value is and add 1 to them, right? Okay, but adding 1 is fixed constant. So the first basic observation is that when computing the value of the ith guy, we want to focus on only indices j such that aj is less than ai, right? So if you just want to think of the numbers in the sequence, those numbers must be less than my thing, and I only want to look at them, right? And binary search trees help us figure out, which numbers in a given set are less than me, right? And which are bigger than, if you want, right? So a natural data structure is a binary search tree. Okay, but that's not enough, right? Because if it's not enough to look at all the numbers less than my value, because I want to find what do I need to find among them? Each of them stores a number, right? Which is the value of the optimum solution ending in that. I want to find among all these guys the maximum. I don't want to just look at all of them because their set itself can be large and then I'll be back to linear time. So I want both of those features. So we'll start with a binary search tree. So we store A1, A2, AK in a binary search tree. Okay. So in a balanced binary search tree to make things faster. So when I'm doing iteration k plus 1, we'll add AK plus 1 to the search tree, right? Okay, we'll insert it. But okay, what do we need? If I have let's look at iteration I. I'm looking for AI, right? I want to find all numbers in A1 to I minus 1, which are smaller than AFI. Can I do that easily with the binary search tree? Yes, I can search for AI in this tree. I don't want to enumerate all of them, right? Because that will take too much. But what the binary search tree will tell me is that, look, this whole subtree is less than, all the numbers in the subtree are smaller than AFI, right? If I look at them, well, that's too expensive. I don't want to look at them. What do I want? I want the maximum value of the optimum solution values in all that subtree stored at a node. Okay, we'll see an example. Okay? And each node in the binary search tree should store what? The maximum of all the optimum values of the things in that subtree. Okay? So let me give you an example. If this is actually, so maybe it'll, and the search tree will, so let's go back to the same thing, right? That sequence we did. I can't remember it. Can somebody, okay, 635, who has good memory, right? Okay, let's make up some number sequence or, okay, okay, we'll make up some sequence. Okay. Okay, so it was some 6, 3, 5, 2, 1, 7, 2, 8, 9, 4. Okay, right? Let's assume without loss of generality that all these numbers are distinct. That will help us. Okay, otherwise, you know, you have to be a little bit more careful. Let's assume that numbers are distinct. So, in some sense, with every index there is a unique number, right? You know, there is no confusion, right? Okay, so the first guy, right? You know, 6. We computed the value 1, right? So what does the binary search tree store? It just stores 6, right? So far, right? It's just a single, right? Okay, now we get 3. Okay. 3, you know, when we try to evaluate 3, what do we want? We look in the binary search tree, you search for 3 in the binary search tree. Okay. Well, I mean, in the base cases are always a pain, right? You know. So, okay, but then, you know, we find that there is no number smaller than 3 in the binary search tree, right? So, we then calculate the value as 1, but then we have to insert 3 into the binary search tree. Okay, how does the binary search tree look after I insert 3? You know, it will look like this. Okay. Okay, then I get 5. When I search for 5, what does 5, when I search for 5 in this tree, what happens? Okay, how does binary search tree searching happen, right? You go to the root, okay, and you say, 3 is smaller than 5. So the left child, the entire left child of 3 is smaller than 5. Okay, okay, in this case it is empty, so I don't get any value. But I get 1, I mean 3 is also smaller than 5, so the value of 3, I add 1, right, I get, 5 will get 2, and then I go right, I also have to go to the right child of 3, right, because the entire left child of 3 is smaller than 5, I have to explore the right child of 3, okay, then I explore the right child of C and immediately I stop, because 6 is bigger than 5, okay, well, no, I don't stop, I check, 6 is bigger than 5, so which means that I have to go to the left child of 6, right. But the left child of 6 is not there, so I'm done, right? So searching for a number in binary search tree takes log n time, wherever it's balanced. You kind of go right? Okay? Okay. So in fact, you know, when you search for 5, where do you insert 5 in the binary search tree? No, I mean technically you should insert it here, right? Okay? No, not there, right? You know, not here. Okay. No, in fact, yeah, that's where you should insert, right? Yeah, right? But it is not balanced anymore, right? But balancing is what you have to rotate and do all that nonsense, right? Right? So let's not worry about that because that somebody can do it for us, right? Let's focus on the basic operations, right? We'll create an unbalanced tree, but we'll worry about balancing later on, right? Okay, but then what happens? Well, we computed, you know, when we search for 5, I claim that we can actually compute the optimum value of 5, right? How? When we search for 3, we know this entire left tree is okay, so to do that, we need to maintain some extra information in the binary search tree. What do we need to keep track of? Okay, when I search for 5, what am I doing? I came to the root, right? What do I know about the left tree of 3? In this case it's not there, but if there is a left tree of 3, what do I know? All the numbers in the left tree of 3 have to be smaller than 5, right? Okay. What does 5 want from that left tree? The max value, right? It doesn't want to look at all of them. I just don't care. I only want the max value of that. Okay. So each tree stores the max of all the children in, each node stores the max of all the values in its children, right? Okay. So if we had that value, then we can compute the optimum value for 5, right? Yes? Okay. Okay. So so what is, at this point, what does 3 store? No, at this, after inserting 5, 3 will store 2. Why? Because the max value in the subtree is, for 5 it is 2. What does 6 store? It also stores 2, right? Okay, what does 5 store? Well, you know, it will store 2, right? They all store 2, right? Okay, now let's insert 2. What happens when you insert 2? 2 comes, 2 comes, what does it do here? It's smaller than 3, right? So it has to go to the left child of tree, and then it finds it's empty, okay? So basically, when you'll insert 2 here, right? Okay? You compute the value of 2 at that point as 1, because you went to everybody who is smaller than 2 and you found there's nobody smaller than 2, so it's just 1, right? Okay, now you insert 1. What happens when you try to insert 1? It'll go to the root, right? It'll have to go to the left, then it has to go again to the left, right? Okay, and you store 1 and you store value 1, right? Okay, now when you insert 7, what happens? What does 7 do? So when you insert 7, it says, aha, it's bigger than 3, okay? Okay, so when it realizes it's bigger than 3, first, you know, it gets at least 2 from this itself, so it's 2 plus 1, it will be at least 3, and then it goes down to see if there's anything better, right? So it goes to 6, and it realizes it's bigger than 6, and then, oh, you can get 2 plus 1, 3, and then it goes down further to the right of 7, and it says nothing there, and so it doesn't get any value better than 3, right? So it inserts 7 here, like the binary search tree does. It's 3, but then we have to update all these values along the path up there, right? Because the max has changed, right? So this guy becomes 3, this guy becomes 3. Okay? Okay? Okay, now what happens when 2 comes? 2, sorry, I made a mistake. I didn't want duplicates. So 2.5, let's call it. Right? You know, I'm just to make duplicates cause some confusion. Okay, okay. 2.5 comes, you know, it basically ends up going to 2.5 will go here, and its value will be what? 2, right? Yeah, and that means that this value will go up to 2, right? Right? By construction, right? Okay, and then what happens when 8 comes? 8 ends up on this side, right? So 8 will end up, okay. Is there a quick way to get to the bottom? I am not sure. Okay. No, I mean, see, I'm just doing it slowly because it is actually a very easy solution, right? Now, 8 goes here and it gets 4 and all these guys go up, right? All right? Okay, okay, now, so on and so forth, right? But the thing is, how much time does this take? Okay, well, if the tree is balanced, when I'm searching for the value, how long does it take? Log n time, right? So, because I'm keeping track of the max along the way, I can compute the optimum value for this guy in log n time. Okay, and then I can go back and update all of them if it changes, right, in log n time. The only problem is it may not become, if you insert like this, it may not be balanced, right? So what do you need to do? You can obviously do the standard balancing operation which keeps everything log n, right? Any of these standard data structures will do the balancing for you in log n time. The only thing you are doing a little different that you have to keep in mind is that, if it is simply a balanced search tree, there is nothing to do, right? Nothing fancy to do. But we are keeping track of this auxiliary information, which is the max under all the bottom things, right? But that's not very hard to update when you're doing the balancing, okay? This is the only thing that I'm going to gloss over, because you have to know the precise balancing data structure you use to see how you can keep track of that maximum value as well. That's not hard, okay? If you actually go back and review your how to maintain red-black trees or 2-3 trees or whichever balancing data structure you want to use, keeping track of this auxiliary information is pretty easy, okay? All right? If you don't have to balance, it's clear, right, that you can do this, okay? So balancing is the only trick balancing is the thing that you need to do to maintain log n time, okay? I've even forgotten all the rotation rules and stuff, because, But okay, the point I want to make, we're running out of time, is that conceptually this is not a hard solution, right? If you have some basic idea of data structures, you say, I can use balanced tree because I want to find only the maximum value and not actually look at all of the things, right? So that's it. So you spend log n time for each guy, so the overall running time will be n log n. Okay? All right? Of course, it means that you need to know some data structures. But that's why we do data structures, right? Okay, that's it. N log n time, n time, okay? N space. But it requires balanced data structures. In fact, there's a very elegant solution which doesn't use these trees, but uses only arrays, and it requires one more clever idea, okay? You have to look, it's not something that is the first order solution, right? But you don't even have to use trees. You can do something very clever. You can find it on the Wikipedia. And when I gave this problem many years ago as a homework, everybody gave that Wikipedia solution. I am sure nobody understood that solution, okay? Because it's actually quite clever, very complicated. But the code, everything was copy of the Wikipedia, right? So what happens sometimes is the solution which is there is actually too clever. What does it mean it's too clever? It means it's something that somebody had to spend a lot of time to come up with. Okay? While the balanced thing, experienced person will do it quickly. That's not the most efficient or elegant solution because it requires you to employ a fancy data structure, right? But it's a conceptually easy solution, in my view, right? Because you say, okay, what do I need to keep track of? Let's see if I can use search trees, right? Well, if you want to use that the Wikipedia solution, you have to spend a lot more time because you are doing something, it's second order solution, right? So, but if you really care about the problem, you can go do even better optimization. I don't want all these data structures. I want something even simpler, and right? Yeah. Okay.